Hello everyone, welcome to Ekeeda platform, and this is Ravindra Jangid here, your electrical faculty, and in this video I'm going to talk about the DC breakers. So I have included some important points which you have to remember while writing your academic exams, and this is also very important points for understanding and in-depth knowledge of the DC circuit breakers. So we'll talk about that. We have already discussed in the previous chapters that the DC breakers are kind of your AC circuit breakers, only the some of the differences can be seen there. Okay, let's see one by one what are the similarity and the differences and what are the actually important points which I have included there. So the first point is saying that the development of HVDC circuit breaker has been underway for the sometime in the late 80s. So in the 80s, late 80s, okay, so there was a development of HVDC circuit breakers was going on there, and that was kind of 500 kilovolt breaker. So that breaker has the voltage value 500 kilovolts. And if I talk about the current interrupting capability, that was up to the 4000 ampere. So voltage is 500 kilovolt and the current interrupting capability is 4000 ampere. Now, although the several types of DC breakers have been developed by the different manufacturers, so at that time the different manufacturers were coming with the formation or the manufacturing of your DC breakers for your HVDC transmission systems, but there were some differences as per your manufacturing, but the basic concepts was same in all the cases and which are written in. Okay, so the first point, the major problem in the current interruption in the circuit breaker is that there is no natural current zero as in the case of AC circuit. If we talk about the AC circuit breaker, that depends on the high resistance and the low resistance value, and in the low resistance value we were using the current that is the current is interrupted on the current is zero value, and according to that we have used the different dielectric mediums, oil circuit breaker, your air blast circuit breaker, SF6 circuit breaker, vacuum circuit breakers we have used there. But that was a benefit of using the AC circuit. But now if we talk about the DC circuit breaker, that is kind of the your constant value. So that is kind of if we talk about the current interruption in the DC circuit breaker, that is a major problem if we compare with the AC circuit breaker. That is no natural current zero. Now, the current can be brought to zero only by applying a counter voltage higher than the system voltage. So it is saying, although there is a problem, okay, we know that is a problem in the AC circuit breaker, that we cannot use the natural current zero in the DC circuit breakers, but there is also a way so we can interrupt that. The current can be brought to zero. Here, if we are using the DC circuit breakers, the current can be brought to zero only by applying the counter voltage higher than the system voltage. If you are making the counter voltage more than the system voltage, then it can be brought to a zero value. And the second problem is that the dissipation of the large energy stored in the inductance of the circuit. So if we talk about the inductance of the circuit, and that the curve is kind of very known to you, that is a basic circuit I am talking about. That is the VD, and there are plus and minus. Here is your inductor, and here is the neutral wire, and there is a switch, okay, current interruption switch, and this is actually represented like this, and this is your VB. This is your VB, and this is the current which is flowing, that is ID, and that is VD is represented here. Now we will talk one by one what is all about that. Now, Consider the simple representation of the DC circuit that I have drawn in the previous slide. It is saying that the breaker has a counter voltage VB, that is kind of that capital V small b, like the subscript, and it can be shown that the energy absorbed by the breaker, which is mathematically represented as. So it is saying the simple construction we have seen in the last slide. So the breaker has a counter voltage. What is the counter voltage? That we have seen in the as a per the switch, and due to this counter voltage, we can make that current to zero. Okay guys, so it can be shown that the energy absorbed by the breaker, which is mathematically represented as, that is kind of the energy, and that is represented as WB, which is equal to 1 by 2 L ID square, and that is VB, that is the VB upon VB minus VD. So this is the basic you can say the formula which is related with the energy absorbed by the breaker. So that the WB is the energy absorbed, 1 by 2 L is the inductor, ID is your current, VB that is the your counter voltage, that is your counter voltage, VD that is the DC circuit DC voltage. Now next, the time required to bring the current to zero. Okay, so as we have talked about, we have to make the current equal to zero. But what is the time for that? The time is actually mathematically represented as follows, and that is your called the TI. This TI is kind of the making the current is equal to zero, and that is L ID, which is VB minus VD. So that is the time required to make the current equal to zero. Now, so where that ID, so this ID is actually this I cap small d is the current in the breaker prior to the interruption, not the interaction, that is interruption, prior to the interruption, and which has a significant effect on the breaker cost. So I think you can clearly relate with that. That is ID is the current, ID is the which current? ID is the current in the breaker which is prior to the interruption. Okay, when the circuit breaker is not interrupting before that. So ID is that current, and which is kind of significant effect on the breaker cost. So that will have the significant on the breaker cost. If it is reduced as, and if it is reduced, so it is going to be reduced as the VB is decreased. WB is decreased. When the WB is going to be decreased, that is the WB. What is the WB? That is the energy absorbed by the breaker. When the energy absorbed by the breaker in the energy which is absorbed is going to decrease, then you can say the current is to be decreased, and the current is to be decreased, then there is you can say the cost cutting will be seen there, and which results in the reduce in the requirements of energy capability of the breaker. So that is kind of the reduction of the requirements for that. Now the current ID, that is ID, is brought down to the rated value by the normal action. So what we are actually doing, we are just making that rated value of current to a normal action of the current control and in the converters. Although this requires a certain amount of time, it will not be at immediate conditions. Okay, never will be that immediate if you're talking about it is increasing or decreasing, because it always involves the inductors. Okay, as we are using the smoothing reactors, that will not be allowed to, that will not allow the current to be decreased or current to be increased as immediate. So that will take the certain time. So it is although this requires a certain amount of the time, approximately you can say 30-50 milliseconds. So what is that? That is the 30 or the 50 milliseconds. I can point out that also, 30 or the 50 milliseconds, and that is the time required for the interruptions and reduces. If this is happening, the time required for the interruptions. Okay, so that's the interruption should be fast. So what happens is the time required to do an interruption is going to be reduced, and that is a good, or you can say the advantage condition for your designing system. Okay guys, now we will move for the some other points. That is saying the counter voltage produced by the arc that is struck when the breaker contacts separate, which is not sufficient in the HVDC breakers. We were talking about the counter voltage which is actually produced by the arc. So that is struck when the breaker contacts separate. When the breaker contacts, it means we will have the fixed contact, we will have the moving contact. So when the breaker contacts due to the fault conditions, when they are separated, when the moving contact starts moving, so this is not the sufficient in the HVDC breakers. This requires an auxiliary circuit in which the capacitor is inserted to develop the required counter voltage. So that is actually for the AC system. If we are talking about the DC systems, so that will require the additional circuit, or you can say the auxiliary circuit, in which there will be a capacitor which is actually inserted to develop the required counter voltage. So that additional capacitor which we are actually using is actually going to provide the required counter voltage there. Okay, now however, the capacitor is unable to dissipate the energy. It cannot dissipate the energy. The resistor is used for that, and the current in the capacitor has to be commutated to the non-linear resistors. So it is clear for you that a capacitor is unable to dissipate. Obviously, it is unable to dissipate the energy, and the current in the capacitor has to be commutated to the non-linear resistors. We are using the non-linear resistors, okay, which then dissipate the energy without due increase in the voltage across them, without the increase in the voltage across them. That will be without the increase in the voltage across them. Now, so if we talk about the arrangement for the DC breaker diagram, that is given here. So here the ID is flowing and it is dividing in the I3, I2 and here the I1. Okay. Now this is the SD and this is the SC, this is the RD, this is the JC, ZC. This is called the commutating circuit. This is commutating circuit. This is called the energy absorbing circuit, and this is the circuit breaker. So this is all about this, and the VD is a kind of here VB, that is a VB, that is the counter voltage. Counter voltage. Okay. Now the current in the breaker, when it is in the closed condition, okay, is normally carried through the circuit breaker with the moving metallic contacts. So I think you can clearly relate with the AC circuit breaker. The same thing is happening here. The current in the breaker, if you're talking about the DC circuit breaker, when it is in closed condition, there will be the moving contact and you can say the moving contact is fixed, and the moving contact both are in the closed condition. So there will be a normalized current is to be flow there, okay, and that is carried through the circuit breaker with the moving metallic contacts, Now this may be a vacuum oil, this may be vacuum oil, air blast, and SF6 device, that is SF6 kind of SF6, okay, SF6 device. These are actually depending on the arc extinction process. So the medium, or you can the insulating dielectric medium which we are actually taking, according to that we are providing the name of the circuit breaker. For example, let us we are using the vacuum to extinguish the arc, or the arc due to the fault condition, then we will call it the vacuum circuit breaker. If we are using the oil as a dielectric medium, then we are going to name it as oil circuit breaker. Similarly, air blast circuit breaker, similarly SF6 circuit breaker. After the trip signal, when it will detect, so who is going to be detect there? there will be a combination of the circuit breaker and the relay. So relay is going to detect there, and it will send the trip signal to the isolators, and the isolators are going to separate that the contacts of the circuit breaker, and the breaker contacts open to draw an arc, and which is initiated at the time t1, and which is shown in the graph. So here it is initiation will happen. Okay, so this is the, you can say, the counter voltage. You know all these things. Okay, so this is the counter voltage, and this way is to be drawn there. So that is the simple curve. Okay, and please go through this. In the passive commutation method, that is not the commutation computation, that is a commutation, that is commutation method. It will use the series LC circuit which is connected across the circuit breaker. So LC circuit, and due to that LC circuit, we have seen in the AC power systems, there were if you have studied about that the circuit breaker in the AC power system, then the thing we have already discussed, that is related with the LC circuit. And the interrupter element circuit breaker is an air blast, and the SF6 circuit breaker, which is kind of similar that we have used in the AC circuit that I have already told you. Now, the field tests have shown that the air blast circuit breaker is superior in performance as we compare to the SF6 circuit breaker. So the field test in the means the practical calculation and the manipulations. Okay, so that if as we have studied for that, then that actually shown the some results, and according to that we have come up with the solution that if we are using the air blast circuit breaker, so it is going to be superior as per their performances if we are comparing with the SF6 circuit breaker. If we are comparing with the SF6 circuit breaker. Now, the computation, not the computation, it is again a commutation. So the commutation of the current to ZC, that is capital ZC, is the passive commutation method, and which is actually initiated by the arc itself. Okay, so if we are that is related with the simple commutation method. Okay, so we have to reduce the current to zero, the commutation of the current to ZC. Okay, and the differential equation for the current I2, differential current I2 is given as follows in the circuit, and which I have shown you. So this is the basic equation which we have to remember there. Okay, and this is the circuit where the L and C are actually connected like that, and there is a kind of a switch, and this is V arc, or you can say the counter voltage which is provided. This is the current I1 and this is the current I2. So this equation is kind of related with the I2, and that is LD square I2 upon let's read that first. L di2 d square I2 upon dt square plus dv arc upon di1 into di2 upon dt plus 1 by c I2. The change in the arc voltage, that is actually it is written that is a change in the arc voltage. Okay, the change in the arc voltage, or you can say the arc voltage, as the arc voltage is decreasing, not the change, as the arc voltage is decreasing with the current, its differential resistance is negative. Then the differential resistance is going to be negative there if you go through that formula, and that is a kind of dv arc upon di1. Okay guys, so this is causing the buildup of increasing the current oscillations in the circuit, and the arc goes to zero there. As we cannot make that current to zero, as we are not having current zero method or the sinusoidal current, because whenever we are having the sinusoidal current value or voltage, sinusoidal oscillations, then we will have the natural current zero, and that is actually not possible in DC. That's why we are actually doing the procedures like that. Now, while this simple explanation of the phenomena, the process of completion is affected by the geometry of the breaker nozzle. Okay, that is depending on the geometry of the breaker nozzle. There's a nozzle from where the arc is to be carried. Okay, if you have studied about any circuit breaker, then a nozzle is provided from the where the arc is there in between the fixed and the moving contact, and from the nozzle there will be the air blasting, there will be the vacuum is provided there. So that nozzle is kind of that. Okay, so that is depending on the geometry of the breaker nozzle. And also the interaction chamber, that is not the interaction, that is the interruption. So that is the interruption chamber. Interruption chamber is simple thing where the arc is to be extinguished. Okay, and the natural frequency and the stray resistance of the circuit. Now, this increase in the oscillation magnitude may also occur in the steps. So that kind of the discrete type, you can say. So these oscillations having the magnitude may also occur in the steps. So that can be occur in the step formation. The current oscillations or current oscillations in the commutating circuit. Okay, so where we have to make that current equal to 0 is kind of shown below. That is a diagram for that. Okay, that is the average DC current, and this is the T2. Okay, and this is the T3. So what is the T2 and the T3? There we have seen the graph. Okay, so here in the T2 from T3, there will be a decrease in the I1 current and there will be the increase in the I2 current, but the DC current is going to be decreased there. Okay, so kind of like that. And now, so this is the simple curve. There will be the kind of oscillations or current oscillations, you can say. I hope you have understood all the concepts which I have discussed related with the circuit breaker. Thank you so much.